In this video, we will conduct a comprehensive bivariate linear regression analysis using Python. One of the tools we'll use in order to do this is the UCI machine learning repository, which contains multiple data sets. But before we get to that, we'll start by looking at a popular data set called the Gapminder data set. This data set contains some interesting information about countries of the world. We'll see the names of the countries. The data come from several different years separated by 5-year intervals. We have population data, and additionally we have 2 quantitative variables, GDP per capita and life expectancy in each of those countries. So it may be of great interest to us to try to understand the relationship between those last 2 variables that I named. Is there some kind of association between the wealth of a country and a measure of what we could say a measure of quality of life or the health of that country, as measured in terms of life expectancy, the average number of years that an individual is expected to live in that country. Okay, so as I go through this lesson, I'll talk about some of the concepts involved in linear regression analysis, and I will also take a close look at some of the Python techniques that we can use to accomplish this analysis. So the first thing that we'll do, as usual, is import the data set from a URL using the readCSV function that's part of the pandas library, one of the most popular libraries in Python. This creates a pandas data frame, which looks something like this if we take a look at the first 6 lines using the head function. We could also take a look at the last 6 lines using the tail function. But here we see the nature of the data. We see the multiple years, population, also continent, life expectancy, and GDP per capita. In early analysis, what you often want to do is do some filtering to settle in on the data that you would like to analyze more thoroughly. So in order to do this, we're going to look at the most recent data. That's a common practice. If we want to understand a phenomenon, it's much more relevant to look at the most recent data, although 2007 seems like a kind of a long time ago at this point. In order to filter out just the 2007 data, we're going to use this filtering approach where we create a Boolean to check whether the year is equal to 2007, and we keep only the values for which that condition is met. Okay, we can take a look at the shape, which gives us the dimensions. The number of rows is 42, the number of columns is 6. As we continue to go through some of the pre-processing tasks, we'll see that all we're doing in this step is helping ourselves understand some of the characteristics of the data set. We can take a look at the shape as we just did. We also might want to take a look at the data types that are contained in this data frame that we've just created. And this is important, especially when we're doing a statistical analysis that relies on having quantitative data. So if I see integer or float, then I know that it's going to be possible to use that kind of data in a statistical analysis, and those values can be used to create a linear regression model, which is our goal with this lesson. Another pre-processing task is to check how many missing values we might have. In this case, we don't have any, which is good. We can take a cursory look at this exploratory data analysis section. This step simply involves understanding the variables individually before we start to look at how they are related to one another. Some of what you see in this code block are the creation of histograms, some customization of the plots that we'd like to create in order to understand the data better. Let's take a look at the graphics. The first two histograms that we've created both look at the distribution of GDP per capita. However, the second histogram takes a look at the logarithm of GDP. This is a common transformation that's done when a distribution is heavily skewed. Now, of course, in trying to understand the distribution of this variable on its own, it's not so helpful to look at the logarithm of GDP. However, this is a supporting step that allows us to perform a linear regression analysis, as we'll see later. So just kind of keep this in the back of your minds, and then we'll come back to it when we start looking at the scatter plots. This section takes a look at a scatter plot between GDP per capita and life expectancy. This is a point where we tend to make a choice about which variable we'd like to be the explanatory variable and which one we want to be treating as the response variable or dependent variable. So we can use explanatory and response as our terms. We could also say independent or dependent variable. We can use the scatter function, which is part of the PyPlot module that comes with matplotlib. And then, of course, we have some customization of our display. The scatter plot is clearly curved, which makes it difficult to fit a straight line model, right? The analysis that we want to do is called linear regression. So that kind of implies a straight line. Now, of course, there are some sophisticated methods that involve polynomial regression. However, if we can make a transformation that will linearize this scatter plot, then we have access to the linear regression functions, which is what we'd like to be able to use. So this is why we made the transformation of the GDP variable. This step is often a trial and error step. If you do a lot of regression analysis, you'll start to recognize certain patterns that would prompt a transformation. And a curved pattern is one that definitely prompts a log transformation. Here's how the scatter plot will look once we do make that log transformation. We always want to take a look at the graphic to make sure that we've been able to effectively turn that pattern into more of a straight line, right? So it does look like we could draw a straight diagonal line through those points. Obviously not perfect. There's quite a bit of variation around the line that we might imagine going through the center of the data, but this would be much better than the curved graph that we saw before. So I feel justified in making that log transformation. Another task we generally like to perform when studying a data set is to take a look at the strength of the association, and we can do that using the value called correlation. We can actually do this quickly for all of the variables. We can take a look and see what are the pairwise correlations among the variables that we have. So we can actually take a look at population as well, even though that won't be part of our final analysis. So what we might notice is that the variables of interest have a correlation of 0.68 if we round. So we see that duplicated. Now, we have a key here to help us understand whether or not our correlation measures a strong association. And I would say that this is probably a moderately strong association between those two variables. We kind of think of anything close to 0 as weak, anything close to 0.5 is moderate, and then anything close to 1 is strong. So it's kind of in between a moderate and a strong association. In our efforts to understand the strength of the association between the variables, we can use an additional visualization tool, which is the correlation heat map. This attaches colors to the correlations and automatically gives us a key to tell us what those colors indicate. And this is built with the Seaborn library. This line in line 4 is totally optional, but that's a way to only show the lower triangle. And that can be useful because the upper triangle would have all of the same information. So this sort of just simplifies the view. The tool we're using is called heat map, and we're referring to the correlations, which is a variable that we just created above. All right, now that we've done a lot of that exploratory analysis, we can now take a look at a regression analysis. We're going to rely on the log of GDP per capita as our explanatory variable, aka independent variable. And we're going to attempt to model life expectancy as a function of that variable. So we'll start off with that transformation, and keep in mind that this entire analysis is between those two variables, one of which is transformed. Okay, so we can do that quickly with a log function that comes with the NumPy library. Next, we want to import the variables that we're going to be using. We're going to import pandas, and we're going to import a specific testing module from pandas. We're going to now import the Statsmodels formula API as SMF. This allows us to build basically the formula that determines the linear regression model. Okay, so the way we use this SMF function is indicated here in line 6. Okay, so SMF is the name of the library that we imported. From within the Statsmodels formula library, we want to use a function called OLS. This stands for ordinary least squares. There are several different types of algorithms that fit the optimal linear model to some data, and this is a common one. So we'll use ordinary least squares. We can specify the model. So the first argument is the formula. The second argument is the data that we want to use. So we do have more than one data frame in this notebook, so we want to be clear in saying that the data is the GM07 data frame that we created by filtering out just year 2007. And then we add on the fit method. So this entire line is really the heart and soul of building the linear regression model using the Statsmodels library. We can print the results, but all the results will tell us is, the name of the object, Statsmodels regression linear model. So it's not especially useful to take a look at the name of the object that we created. We'd much rather take a look at the summary. So we can look at the summary, which will tell us a lot of that information that helps us understand the relationship between the variables that we're studying, and also some information about how well this model might perform on new data. Some of the pieces to highlight from this regression output are the R-squared value, which we will take some time to interpret. We also care about the coefficients, which determine the position of the model and allow us to make predictions for data that's not included in the model. We also have some results having to do with the inferential considerations of this model. Basically, whether or not the results are statistically significant. So we'll talk a little bit about what the outputs mean. Let's move on to some language for interpreting the regression output. One of the things we care about quite a bit is the value of the slope. And here's a place where it's going to be important for us to remember that we're dealing with log of GDP. That's our transformed variable. The slope tells us that for each unit increase in the log of GDP, the model predicts a 7.2-year increase in the country's life expectancy. And I got that, where did I get that 7.2? I got the 7.2 from right here, okay? So our coefficient, our slope, is always going to be telling us the predicted change in our dependent variable for each unit increase in our independent variable. So that's why I said for each unit increase in log GDP. This is the predicted increase in the country's life expectancy. All right, we also care about the R-squared value. The R-squared value is about 65. It's usually presented as a percentage. And the way that's interpreted is it's the percent of variation in life expectancy that is explained by the linear regression predicting life expectancy from log of GDP. That's kind of the long interpretation. A shorter interpretation would be it's the percent of variation in the dependent variable explained by the model. Okay, and this basically just means that there are many other factors that could be contributing to a country's life expectancy being large or small, and you can probably easily think of what those variables might be. Now on to the p-value. In this case, the p-value is approximately 0, and that actually is a good thing if we're hoping to identify a relationship between variables. A small p-value close to 0 in this case means that the observed relationship is unlikely to occur by chance, and it's much more plausible then to conclude that the relationship that we observed is actually coming from a meaningful phenomenon rather than being due to random chance. So again, a small p-value supports the claim that there is in fact a real relationship between these variables and it didn't just happen by chance. When we finish up a regression analysis, it's always good to write a few sentences explaining what we've been able to discern from the analysis. And that's what these last few sentences are aiming to accomplish. So we could say the regression output helps us quantify the relationship between the variables and evaluate the model as far as its usefulness for predicting life expectancy from GDP. The p-value tells us that the linear relationship is statistically significant. The R-squared value tells us that the linear model predicting life expectancy from GDP explains 65% of the variation in life expectancy. So in general, when we encounter a low p-value and a high R-squared value, that's pretty strong validation that the model is appropriate and meaningful for the data. It's possible to see cases where you have small p-values but also a small R-squared value, and in those cases that indicates that the relationship between the variables is meaningful. It didn't just happen by chance, but the model would not perform well on new data because there's so much random variation that's unexplained. Lastly, we can take a look at one final task, which would be fitting the model to the scatter plot, drawing a visual to approximate the relationship that we have quantified here. So there is some code included for doing that. We're going to be using the polyfit method. So we've imported from the NumPy library, we've imported the polynomial fit module. That gives us the values for the slope and the intercept. So then those are numbers that we can plot, and that's what we do in line 15 here, where we plot our x values, which remember those are our GDP per capita, and then we can type out the model. And remember, this is just y equals mx plus b. It's just reformatted because in statistics we usually say b plus mx because we just have to be different. So the b represents the intercept of the model, the m represents the slope of the model, and so what we're doing in this line is calculating all of the predicted values. The dash just says what kind of symbol we want to use for visualizing that line in the plot that we create. So when we run this, we get a nice visual showing the approximated relationship between life expectancy and the log of GDP.